So here we are again with the module 2 of the chapter 1, that is electric fields. So what are electric fields? We will discuss here. Let us consider a positive charge, this, around which there is a region we can see here. About this region there are two charges, one negative charge outside this region and one positive charge outside this region. When these charges are outside this region, then these charges experiences no force. But when these charges come within this region, this negative charge experiences a kind of attraction force and this positive charge experiences a kind of repulsive force. And if these charges were outside the region, there was no any kind of force between these two charges or these two charges. It means when these charges are within this region, they experience a kind of attraction or repulsion force, and within this region they can experience only. So this region is termed as electric field. So we can say that the region around a charge in which another charge experiences an electrostatic force of attraction or repulsion is called its electric field. Moving ahead with some more about electric field, that is electric field lines. Watch here. Here we can say a positive charge. These lines are representing the direction of the electric field. At this point, the direction of electric field is this. At this point, the direction of electric field is this. At this, like this. At this, like this. So at each and every point, these lines are representing the direction of the electric field, and these lines are called electric field lines. In the same way, here for a negative charge, these lines are representing the direction of the electric field, so we can say them the electric field lines. So we define them: the line drawn at any point of the electric field which represents the direction of the electric field at that point is called electric field line. So moving ahead with some more about electric field, that is properties of electric field lines. Let us discuss. I am watching here a positive charge around which there are the electric field lines. These electric field lines can never intersect each other. These are separated like this. For the negative charge also, the electric field lines can never intersect with each other. They are separated. So we can say that the electric field lines never intersect each other. Moving ahead, the next property. Watch here. The electric field line is always perpendicular to the surface of the charge. Here we can say, we can watch here and we can say that the electric field line is always perpendicular to the surface of the charge. That is, the field lines are perpendicular to the surface of the charge. Moving ahead to the next property. Watch here. This is a positive charge, and from positive charge the electric field lines are originating. Positive charge is the source for the electric field lines. These are originating from the positive charge. So we can say the start point of the field lines is at the positive charge. Moving to the next point. Watch the negative charge. These electric field lines are ending at the negative charge, meeting at the negative charge, or negative charge is the final point for the electric field lines. So we can say that the end point of the field lines is at the negative charge. Moving to the next property. Watch here. Here I can see a small charge which is associated with some electric field lines. Next one, a bigger charge which is associated with some more electric field lines. And the next one, The largest one is associated with the largest number of electric field lines. In this way, we can see that higher the amount of the charge, higher the number of electric field lines. So we can say that the number of field lines is directly proportional to the magnitude of the charge. So moving ahead with the electric field lines, watch here. Here I can see a positive charge in contact with I have a negative charge, a nearby negative charge. What happens? The electric field lines originates from the positive charge and finalizes at the negative charge, from positive to negative, from positive to negative. In the same way, if we bring together two positive charges, then what happens? These electric field lines clash together like this. So we can summarize these properties of electric field lines like the electric field lines never intersect each other. The field lines are perpendicular to the surface of the charge. The start point of the field lines is at the positive charge. The end point of the field lines is at the negative charge. The number of field lines is directly proportional to the magnitude of the charge. So these were the properties of the electric field lines. Moving ahead with the electric field intensity. What is this electric field intensity? Let's discuss. Let us consider a charge positive Q. In the electric field of this charge positive Q, there is another charge which is the test charge Q0, which is also a positive charge. So there will be a kind of repulsive force between them, and this charge Q0 will be repelled with a force F. So this is our consideration. If the force experienced by the charge Q0, this one, in the electric field, this one, is F, this one, then the electric field intensity will be given as E is equal to F upon Q naught. So this will be the expression for the electric field intensity. Vector E is equal to vector F upon Q naught. So this is our expression for the electric field intensity, and the electric field is represented by vector E. It is a vector quantity, and the unit of the electric field intensity is Newton per Coulomb. From here we can see force, the unit is Newton, charge Q0, the unit is Coulomb. So the unit becomes Newton per Coulomb. Moving ahead with some more about electric field intensity, and that is electric field intensity due to a point charge. So let us consider a charge positive Q and a test charge positive Q0 separated by a distance r. This positive charge, which is a test charge Q0, experiences a force F, which is the force of repulsion, the electrostatic force of repulsion. So the force between Q and Q0, this Q and this Q0, will be given as this from the Coulomb's law. F is equal to 1 upon 4 pi epsilon naught Q0 upon r square. And we also know that the electric field intensity due to the point charge is given as E is equal to F upon Q0. So we will put this value of F in this equation, this value of F in this equation to get the expression for the electric field intensity due to a point charge. So let's see what we do. So this is the system of the charges. This is our formula, E is equal to F upon Q0. We need to put the value of F. So put the value. Putting the value of F from equation 1. What happens? This happens. 1 upon Q0, this Q0 as it is, and the value of F is this 1 upon 4 pi epsilon naught Q0 upon r square. This Q0 will be cancelled by that Q0, and we will get E is equal to 1 upon 4 pi epsilon naught Q upon r square, and this is the expression for the electric field intensity due to a point charge. Moving ahead with some more. These are electric charge densities. What are these electric charge densities? Let's discuss. First one is linear charge density. Let us consider a rod of length L on which the charge Q is uniformly distributed. Then the linear charge density will be given as lambda is equal to Q upon L. Lambda is the linear charge density, Q is the charge distributed, and L is the length of the rod. So we can say that the charge present per unit length of a rod is equal to the linear charge density. So we define this as the charge present per unit length of a rod is called linear charge density. The unit of linear charge density we can decide from here. The numerator is charge, the unit will be coulomb. The denominator is the length, the unit will be meter. So the unit will be coulomb per meter. And we can see here it is represented by lambda with the unit coulomb per meter. Coulomb per meter. Moving ahead with the next charge density, which is surface charge density. So let's see. Let us consider a surface area A on which the charge Q is uniformly distributed. So the surface charge density will be given as this: sigma is equal to Q upon A. So we will define this like the charge present per unit surface area is equal to the surface charge density. We can define it like the charge present per unit area of a surface is called surface charge density. In the same way, we can decide the unit of this. The numerator is the charge, that will be coulomb. The denominator is the area, so the unit will be meter square. So the unit will be coulomb per meter square. Watch here. It is represented by sigma with the unit coulomb per meter square. Coulomb per meter square. Moving to the next charge density, which is the volume charge density. This. So let us consider an object of volume V on which the charge Q is uniformly distributed. So what will be the volume charge density for this object? Let's see. Rho is equal to Q upon V. Here we can see the charge per unit volume present on an object is equal to the volume charge density. The charge present per unit volume is equal to the volume charge density. So we can define it like the charge present per unit volume of an object is called volume charge density. In the same way, we can decide the unit of this. Numerator is the charge, the unit will be coulomb. The denominator is the volume, the unit will be meter cube. So the unit will be coulomb per meter cube. So we can write it like it is represented by rho with the unit coulomb per meter cube. Coulomb per meter cube. So that's all for today. See you again. Thank you for now.